The recording. Hello and welcome. Our project is about increasing accuracy in Memristive chips for analog image recognition. We're Team 38, and this is our senior design project for Arizona State University. Let's meet the team.
Hello, I'm Hoyer.
Hello, this is Wataru.
Hi, I'm Benjamin.
I'm Justin.
And I'm Zach. Our mentor is Dr. Matthew Marinella. To introduce you to our project, it mainly focuses on improving the long-term reliability of Memristive chips for image recognition algorithms. Memristive chips are an analog computer chip that does mathematical computations in memory. They are a low-power alternative to digital computer chips and are commonly used to perform massive amounts of multiplications for AI and machine learning programs.
Let's get into the problem statement. The Memristive chip, they are especially vulnerable to radiation. So the memory is stored in the form of the trapped electrons. The exposure to radiation will eject more and more electrons over time. We call this conductance drift. So this finally this leads to worsening the accuracy in computation over time.
The effects of this conductance drift on the chips are the total ionizing dose, or TID, is the accumulated amount of radiation exposure the chip receives. Higher TIDs directly correlate to lower accuracy in image recognition programs.
To help account for this drift, we use an alpha correction factor, which is calculated for every layer of the network. And the idea is that if we were to multiply the output of the matrix vector multiplication by 1 over alpha, we can correct for the conductance drift to improve accuracy. As you can see, before the alpha correction factor, the dot products are not super accurate, but after the alpha correction factor, especially at lower TIDs, it is able to more or less correct for all the errors caused by the increase in the total ionizing dose. And before was the dot products, now we create a ResNet32 model to demonstrate whether or not the alpha correction will actually work on the full network. And as you can see, when we don't use alpha, there's a roll-off around below 10K TID, but using alpha, we're able to get extremely close to baseline accuracy, well beyond the limits that not having the alpha correction factor would have.
The second method is training with noise. The procedure includes injecting noise into the neural network training, results in a model that improves after being exposed to radiation, but has worse performance when brand new.
In conclusion, we have successfully implemented methods that improve the long-term performance of Memristive chips by adjusting multiplication values to account for error, as well as training models to prepare for eventual exposure to radiation. Thank you.
Thank you.
Thank you.
Thank you.